the satisfiability problem, which is one way to think about it was you have a circuit, a Boolean circuit with AND, OR and NOT gates, and the question is, do there exist a collection of inputs so that the final output gate is 1? So that was Boolean satisfiability. Then we said that this problem reduces to 3-SAT, which is another satisfiability problem but with a very special form. Okay, so it was the AND of a bunch of clauses, and each clause had exactly 3 literals in it. Okay, so it had it was an OR of 3 literals. So that was 3-SAT. Okay, and the idea was that this general form of satisfiability reduces to this very special form. And then we saw this transformation of every instance from one problem to another. And then we said, the reason we care about 3-SAT is that you can then use this as a starting point for hardness reductions. So we said that we saw a reduction from 3-SAT to independent SAT. And just to recap, so this basically means that 3-SAT is harder, right, or at least as hard as SAT, right? So that's why we use this less than or equal to type notation. It's just to make things clear. Okay, and one thing to remember is that the transformation itself is unaware of whether the formula is satisfiable or not, right? Like you have a 3-SAT instance, just you need to look at the instance and come up with an instance of independent SAT. Okay? So you know nothing more about this instance. You don't know if it's satisfiable, if it's not. And that's the point. And I said that some reductions are easy, but often reductions are somewhat of an art. Okay? So you have to know what NP-hard problem to reduce from, and the reduction itself could involve some tricky gadgets and stuff like this. So this is what I said. And I also said that there's this other problem called subset sum. So NP hardness is not, it's not just for things like satisfiability or some graph problems like independent set. Even numeric problems, some of them could be NP hard. Okay, so one was this problem where you are given a bunch of integers and some target, and you want to know if there's a subset of these things whose sum is equal to f. Sum is equal to this target. We said that in general, each writing down these numbers could actually be roughly n bits long, and this is roughly what makes the problem NP hard. So we didn't prove this. We are not going to prove this, but this is just an example of a seemingly simple problem that's NP hard. Okay, so like a simple numeric problem that is actually NP hard. Okay, so today I wanted to continue with one thing about NP completeness, which is what about optimization? Right. So far we've just restricted ourselves to decision problems, right? Like yes/no answers. But almost all the problems we've studied in the course are actually optimization, right? Like minimum spanning tree, shortest path. Everything is you want to maximize or minimize something. Okay? And we said that one way to convert an optimization problem to a decision problem is to say, is the answer more than a certain amount? Okay? And then you could binary search for that threshold. Right? But then sometimes we might just be interested in an approximate answer. Okay. So for instance, I could give you a graph and say, hey, I'm interested in the size of the maximum independent set, and I'm okay if you're a factor 2 off. Okay. We've seen algorithms like this, right? Like for matching, we said that local search gives you an algorithm that's like 2 factor off. Okay. So you could imagine such things for like really hard problems as well. Okay. And so the question is, so we understand NP hardness and stuff, and is it possible that it's NP hard to even approximate certain problems? Okay, so is the question we are trying to get at clear? So we want to say that, we want to make statements like, oh, here is this problem, let's say independent set. We want to say that even approximating it to a factor of, let's say 10 is NP hard. Okay, and And the question is, what does it mean to do a reduction in this case? Right, because so far everything we've seen about reductions was essentially this, right? So we had decision problems. We said you transform one instance of problem A to an instance of problem B. So that it's a yes instance if and only if it's a yes instance for the other problem. So how would you think, any guesses on how you might want to do a reduction? Let's say I have, I want to show it's NP hard, so I want to reduce SAT to this approximation problem. So the question is, how do we reduce SAT to an approximation problem? Okay, so any things? Yeah.
Could we say if it falls within a range? So for the satisfiability to be from here to here, and then be yes or no?
Can you explain that?
So I'm just thinking that with a satisfiability problem, there's a bunch of booleans, and so that's pretty binary. And you expand the options to say that there could be some leeway in terms of what could be false or true within the satisfiability, so that there's not as much stringent restriction.
Yeah, so that's kind of what we'll see in a bit. Okay, so I think what you're trying to say is that maybe let's try to first prove that, distinguishing between a formula that's completely satisfiable and a formula that's 99% satisfiable is NP hard. Is that what you're trying to get at? Where by 99% satisfiable you mean that almost all the clauses, like 99% of the clauses, are satisfied. Yeah. So sure, if this were hard, then okay, I could imagine reducing it to other problems, right? But how do you first prove that this is hard? So what is, like, suppose I want to reduce SAT to this problem. Okay, so like regular SAT, deciding if it is satisfiable or not to this approximation problem. Did you have an answer? Oh, okay. So it turns out,
I was going to say, can we add some sort of probability qualifier on our reduction, right? So if it's a yes with probability of somewhat, would that give us any more expressiveness or power to?
Well, that's an orthogonal thing, but sure, then you could say, okay, most of my instances that I get are probably, are yes and stuff, but it doesn't quite get to an approximation, right? But so most of the time it might. So the idea is to, it turns out it's actually very simple. Once you see it, you'll say like, oh yeah, this is the way to do it, and so it's what are called gap reductions. Okay? And the idea is the following. So suppose I stick to SAT and independent set. Okay. So what I will do is we want reductions. Okay, so we want a reduction that takes yes instances of SAT to instances where with max independent set being bigger than or equal to, let's say, some 10k for some k, and no instances of SAT to instances with less than or equal to k. Okay, and this is what is called a gap reduction, and you might say, how do you come up with such a reduction? But that's a different question, right? But the idea of gap reduction is, so I want to draw a new picture. So earlier we had this picture of a reduction, right? So you had two decision problems A and B, and and everything was yes here, yeah, and no, yeah, everything was yes or no. We said that the reduction is supposed to map one instance IA out here to only to the yes ones and no ones to the no ones. So that's what a reduction is ordinarily supposed to do. A gap reduction essentially starts with a yes-no problem like SAT. Okay, so SAT, which is yes, no. And then now you have all instances of independent set. And you have some instances where IS is bigger than or equal to some 10k. You have some instances where IS lies between 10k and k. And you have other instances where IS is less than k. So this is, I mean, any problem you can say instances fall into something like this, right? So you either have the optimum bigger than something, or optimum is some value, right? So any optimization problem, it has some classification like this. What we are saying is we are looking for reductions where somehow all yes instances go to this portion and all the no instances go to this portion. There's nothing that goes to this. So that's why it's called a gap reduction. So is the notion of a gap reduction clear? So it's, yeah, so you might, I'm not telling you how to come up with a reduction. Okay? So in fact it's very difficult to come up with such a reduction. But this is what we would like to do. So and now, if we could have a reduction of this kind, I want to say that approximating independent set to a factor 10 is NP hard. So do you see the why? This is actually simple reasoning, so you should be able to see why. So suppose I have a reduction of this kind that takes SAT and comes up with an instance of independent set with the property that if it's a yes instance of SAT, you go to that area, no instance of SAT goes to this area for some k. Okay? So suppose you had this, then I want to claim that approximating independent set to a factor 10 is NP hard.
If not, we can solve it because the gap, because the 10k gap between initial, we can suppose that we find an approximation algorithm. By this we can reverse the function and solve that.
What do you mean reverse the function? I mean, this is you take one instance of set, you come up with an instance of independent set, right? So how do you use, so I guess what you would like to say is, I want to use the approximation algorithm for independent set to actually solve SAT, correct? So that is the intuition behind reductions. Like, if you want to say that is, approximating that is difficult, then you want to say, okay, if I could do that, I can solve SAT, right? So, suppose I had a factor 5 approximation. Suppose there exists factor 5 approximation for independent set in polytype. Can you now solve SAT in polytype? I'll let you ask questions because there should be. So is the question clear? So I am telling you there is a reduction of this kind, okay, which takes yes guys to those, no guys to those. I'm saying suppose there exists now a factor 5 approximation for independent set, which runs in polytime. I'm saying SAT then can then be solved.
Is k just some arbitrary constant?
Yeah, so K, think of it as something that depends on the size of the saddles.
Okay.
So, yeah, so I need to, both are independent, are infinite sets, so I have to be a bit more careful drawing this. Think of the left side as all SAT instances of a particular size. And yeah, K depends on that size. So actually then I guess the question I should ask you is, what does it mean that there is a factor 5 approximation for independence?
It's within factor 5 of the correct answer.
Okay, so this is a maximization problem, right? So if the correct answer is something, then what do you say? What can you say about the output of the algorithm? Suppose the correct answer is some k prime. So then what can you say about the output of the algorithm?
It's going to be within factor 5 of k prime.
Correct, which means what? I mean, this is a maximization problem, right? K prime is the largest independent set. So what does it mean within factor 5? Yeah, so if opt is, so if the optimum is k prime, then you have at least k prime divided by 5. So that's the guarantee that the factor of 5 approximation gives you. Okay. So now, suppose I had a yes instance for SAT. Now I know that my reduction is going to take me into this space, right, into this zone, right? So what is my approximation algorithm going to tell me? Like, what is the size of the independent set I'm going to get in that case? Can you give a load bound on the size of the independent set? Right?
So if we run approximation by factor 5 for independent set, we can show that the size is at least 2k.
Right, so if I take an instance here and I map it here, so these are all instances where the maximum independent set has size at least 10k. Now a factor 5 approximation is supposed to at least have an answer that is 1/5 of that. Right? So 1/5 of 10k is 2k. Okay, so start with a yes instance. If I had a yes for SAT, then transformed instance we can find an IS of value bigger than or equal to 2. What about if your instance was a no for SAT? What does your algorithm on the transformed instance tell you? Why is it less than 5k? I mean, could it be k? I mean, could it be 2k, for example?
No, it's less than k and it's in the factor of 5. So the optimal solution is at least a minimum of 5, but it has to be in the factor of 5. So error allowed is 5 times of that.
Error allowed is 5 times of that, but this is a maximization problem. Right? If I tell you the maximum independent set has size k, how can any algorithm, no matter what it does, give you an answer that's more than k? So no algorithm can give you an independent set of value more than k, because I just told you the maximum independent set size is k. Okay. So if it's no for SAT, your algorithm as well as any algorithm in the world can only give you value less than or equal to k. So now do you see where we are going with this? So if it was a yes instance, your algorithm gave an independent set of value at least 2k, and otherwise your algorithm gave you value less than k. So now what's the test? And this is the test. Yeah. So you basically say, okay, if I have, I take my instance of SAT, put it through this transformation, I get an instance of independent set, use my approximation on it, value I get is at least 2k, then I know for a fact that I have to be in the yes case. Because no case, there's no way I could have come up with an independent set of size 2k. And that's it, right? So that's why if you can solve independent set to a factor 5, then basically p equals np. Okay, then you can solve SAT. So that's essentially the reduction. Okay, so this is why people look at gap reductions, because essentially, how you come up with these reductions is tricky, but in some sense they let you say that approximating the problem on the right is difficult.
Can you just explain a little bit more briefly how P became NP?
Oh, because you could solve SAT efficiently using the SAT. Yeah.
Why for the no is less than equal to p without the
Two factor.
yeah, without the division by the factor?
Oh, right, because see, your algorithm, all you know is that it's at least 1/5 of the optimum, right? It could really be the optimum, right? Maybe your algorithm was very lucky on this instance and it actually outputs the right answer. Do you know that even the right answer is at most k? Okay. So because the size of the maximum independent set in the instance that's produced is less than k. Okay, so no algorithm, no matter how clever, can actually produce an answer that is more than k. Okay. So that's the definition of the maximum.
But at the same time, if we are lucky in the yes case, we can reach 10k.
Yeah, you could actually reach 10k, but that's great because my test is just that is the value that the algorithm found at least 2k. Does that make sense? Yeah. Of what? Of why we need to do the gap reduction?
How we need to do the gap reduction of the
Oh, yeah, so you want to show that it's hard to approximate this problem, right? Independent set in this case. You want to show that so our goal is this, right? So we want to say that unless P is equal to NP, there is no factor 5 hardness for independence. Factor 5 approximation algorithm for independence. Okay. So that's our goal. We want to prove a statement of this kind. So, why we want to prove is, it's subjective, right? So, I would like to show that, I can't even hope to approximate this problem, right? So, because NP hardness throughout dealt with yes-no problem. Now we are asking if you had a real-life optimization problem, could it be that, you can't even approximate it? Okay, so let me tell you that there are some cases in which these kind of things are very easy. Okay, so one is, if you guys remember this CD packing problem from your second homework, so that's what's called bin packing. Okay, so you have a bunch of songs. Okay, and let's call them L1, L2, up to Ln. And your question was pack them into CDs of a certain length, of certain capacity C. capacity C such that number of CDs. Okay, so this was the problem that you guys were trying to solve. Right, so now I want to say that I can start with some NP-hard problem. Okay, I'm not going to tell you what it is. And maybe I didn't introduce what it is, but introduced a very closely related variant. But yeah, and then I'm going to say, yeah, these are instances of bin packing. Now I'm going to say that yes instances here, I want to get a reduction where yes instances here go to the value more than or equal to 3, and no instances go to value less than or equal to 2. Or something like this. I think it's actually the other way around, but let's not be too specific there. So, right, so actually, yeah, it's actually the other way around. So let me. Okay, so yes instances go to value less than or equal to 2, no instances go to value bigger than 2. Okay. So again, telling yes from no is now equivalent to approximating this to a factor of 3 by 2. Right? Because, that's why I'm saying this is an easy case, because you could argue this is kind of we are cheating a little bit, right? I mean, we know that the answer is an integer, so that's why it's either 3 or 2. Right? So it can't be 2.5. Right, so, but this is just an example. Okay, so I want to tell you that sometimes gap reductions are natural. Okay, so yeah, so can you guys think of which problem you would reduce from here? So what is the only problem that looked like this that we just saw was NP-hard? Yeah, subset sum, right? So there's there's a variant of subset sum which is called partition, where you want to divide a bunch of numbers so that the sum is exactly half the total sum. And it turns out you can reduce partition to this what is called bin packing. Okay, so partition basically asks if you have a bunch of numbers, do there exist a subset? Can you divide it into two equal parts? Two parts that have the same sum of the lengths. So you have a bunch of, so let me just write it in the slide where we had subset sum. So it's a partition problem. Can you divide uh, 1 through n into two groups, into two sets, new partition to two sets S and S complement, such that sum over j in S of aj is equal to sum over j in S bar aj. So that's the partition problem, right? So I mean, essentially it's like saying if I have 1, 2, 3, 4, then I could say, oh, 2, 3 is one partition and 1, 4 is another. Right? And both of them add up to the same. Okay, so that's it. They don't need to be sets of equal size. It could be anything. Okay, so it turns out this problem is also NP-hard, and this immediately implies that this bin packing is difficult. So we won't see this. I mean, this is actually, it's not even worth a homework problem. Okay, so it's easy for you to check. Okay. So this we'll see. But now, so what I want to mention about this example is that sometimes getting gap reductions are actually kind of easy because your answers are discrete. Okay, like in this case, the answer is either 2, or if it's not 2, it has to be at least 3. So that's why, some problems are easy like this. But coming up with gap reductions can often be very difficult. For instance, for SAT, for a long time, for like 30 years or something, it was a major open problem. See if you could come up with some kind of a gap reduction. Okay, so what I mean by that is, so let me mention this. So in the early 90s, there was a big breakthrough result in theory, and this is what is called the PCP theorem. And what they showed is that so PCP stands for probabilistically checkable proofs, which is a completely different story. But that's how the theorem was kind of obtained. But the theorem itself, you will be able to understand. What they show is that 3SAT reduces in Pauling time to what is called gap 3SAT. Okay. So to state the problem is very easy, right? So what it means is that I have this yes-no problem, which is 3SAT, and there exists a reduction from this to what is called as gap 3SAT. So these are again 3SAT instances where you have something of the following structure, where you have here you have instances so instances where the let me write one more value, max SAT bigger than or equal to, actually you can just write equal to now m. This is instances with SAT lying between m, less than or equal to 0.99 m, and this is instances with this thing being less than 0.99. And what do I mean by max SAT? Max SAT value, it's basically if I am given a 3SAT instance, try to see what is the maximum number of clauses I can satisfy, okay, by any assignment. Okay, so it's so that's what's called the max SAT. So it's given a formula, 3SAT formula, which looks like this, right? C1 and C2 and Cm. So here, I mean, it's like saying you want to satisfy all of them, right? So the maximization version of SAT is where you want to satisfy as many as possible. The maximum number you can satisfy is what is called the max SAT value. Okay. And what they showed is that approximating this max SAT value up to some constant, right? So in this case, the constant is 1 divided by 0.99, which is a very close to 1 constant, but even that was not known, right? So for all, I mean, what this guarantees is that telling between m and m minus 1 is difficult, right? But 0.99 m is significantly better than m minus 1. Okay, so that's why this was such a non-trivial theorem. It took like several years of effort to actually prove this statement. Okay, so yeah, this is just an FYI. So if you don't fully understand it, it's fine. Okay, so but this is what's called the PCP theorem. This was a big breakthrough in the 90s. So right, and now you might say, okay, so I have proved that this 3SAT problem is difficult to approximate to a factor like 1.01. What does it tell me about my favorite problem, like let's say independent set? Right? So it turns out there's this cool technique called hardness amplification, where you can say, oh, suppose my problem is hard to approximate to a factor of 1.01, then it's also hard to approximate to a factor of, let's say, 100. So you will see an example of this in the homework. It's a remarkably simple thing, so you will see an example of this in the homework. So mean, it's once you see how it's done. I mean, if once you see the steps in the reduction, you'll realize, oh, okay, that's a nice way to do it. So it's a pretty simple way to do things. So it amplifies hardness. Hardness factors. Okay, so if you start with the assumption that 1.01 approximation to independent set is hard, and you go to 100 approximation to RSE. Okay. And the way you do this is actually, as you will see, it's pretty straightforward. Alright, so this is essentially what I wanted to say about proving hardness results and complexity. Okay, so there are many problems that we'd like to study, and first you should try to get a sense, okay, can I hope to solve this problem in polynomial time? That's what you should try to do. And usually one way to do it is to say, okay, can I easily see some reduction from some NP hard problem to my problem? Sometimes you might, sometimes maybe it exists but you don't see it, right? So, but that's fine. Okay. So that's why we study hardness results in algorithms classes, because we want to be aware that there is this thing. Some problems are just you don't hope to solve it. Alright, so moving on to more positive results. So I'm going to start, today we'll start looking at randomized algorithms. Okay, so this is the next small chunk of the course. So if you guys, some of you may want to brush up on probability. So one of the problems in the last homework was meant to do this, right? So hopefully you guys have brushed up on probability. Like the distance question was supposed to kind of make you guys brush up on some basic probability. So hopefully you guys have done this. Okay. So alright. So what do we look at in randomized algorithms? Right? So the basic question is, can random choices help in algorithm design? What do we mean by help? I mean, we just mean increase efficiency, right, of some sort, space, time, whatever you care about. So that's the general high-level question. So, and to the best of our knowledge, the answer to this is yes. But this, like P versus NP, we don't know how to prove. Okay? So this is one of these. There are many people who believe that the answer is actually no. There are many serious people who believe the answer is no, but we don't know, right? So that's one of the big questions also. This is what's called the P versus RP problem. RP stands for randomized polynomial. Yeah, so that's the thing. But we want to understand at least, okay, so here are cases in which it actually helps. It seems to help. Okay, so maybe that's a very clever deterministic algorithm, but so, alright. And so this is one thing we want to see. And another thing is, what does it mean to be correct most of the time? Okay, so that's one thing we'll try to get at by looking at all the examples. Okay, so randomized algorithms usually come with this guarantee that your algorithm will have a certain runtime and it will be guaranteed to be correct with a certain probability. That's the kind of results we will try to show. Okay, that algorithm is correct with probability at least something. And clearly you want it to be close to 1. And there's always this implicit assumption in randomized algorithms that this is somehow good enough. Okay? So I mean, there might be situations in which it's not good enough, but you know, maybe most of the time in practice that's fine. Right? It's like 0.999 is good enough, right? So something like this. Okay. So, and there's also this thing that we will see. So for some of the algorithms we see, even the running time won't be fixed. So the running time could actually, you could have a large running time with some probability. Okay, so we'll see trade-offs of this kind. Okay, so there will often be a trade-off between runtime and probability of correctness. Okay, so for instance, you'll see that, oh, okay, if I run for a little bit longer, then I can be correct with way more confidence. Okay, so that will be the kind of results that we'll get. Okay. And can you guys think of, what is the most obvious thing where these kind of things come across? This trade-off between running time. Have you guys seen things like this?
Quicksort uses the randomized.
Yeah, so quicksort is a good example. Yeah, so here also, the running time is probabilistic. We'll see. The easier thing you must have all seen is sampling, right? So if you have a bunch of numbers, you sample some of them and compute the average or something. Then the more you take, the more expensive it will be to sample, but the more accurate your result will be. So this is another example which many of you would have seen. Okay. And another example is quicksort. We'll actually see median finding, which is the same thing, in a little bit. So that's what we want to get at. Okay, so these are kind of what you should keep in mind when you're thinking of randomized algorithm. Okay, so you've got to think, okay, what is the probability that you are correct, and what kind of trade-offs do you have between the running time and the probability of being correct? And often you will be interested in the expected running time, which we'll get to in a bit. Alright, so let's start with a very toy example. Okay, so I give you an array 1 through n, and I tell you that at least half the entries are 0. Your goal is to find one such entry, where a of I is 0. Okay, so our goal is find some I such that a of I is 0. Okay, so you are told that at least half of them are 0. So this is one example in which, in this case, no deterministic algorithm that just has black box access to the array can hope to do anything, right? Because if it has just black box access to the array, then you ask queries in some order. Maybe everything, all the first n over 2 of them are all zeros and are all ones, and then you have zeros. And then there's nothing much the deterministic algorithm can do. So, I think you've seen examples of this also in homework 1. So that's. So now, what would you do as if you wanted to come up with a randomized algorithm? Yeah.
Choose a random number between 1 and an integer, and then see if that element is 0 or not.
Yeah, so you can just say, oh, okay, I'm going to pick a random index I and check if a of I is 0. Keep repeatedly doing this, right? So the trivial algorithm, the easy randomized algorithm is pick random I in this range 1 through n and check if a of I is 0. If not, repeat. So note that this algorithm could in principle take infinite time. You could be unlucky every single time. So this is where I was talking about this trade-off between the probability that you succeed versus the running time. So now what we want to understand is this, right? So is the success probability versus time. Suppose you ran this algorithm for precisely one iteration. Okay? So suppose this algorithm ran for exactly one iteration. What is the probability of success? Okay, so it's at least half. So let's say it's half. Okay, so let's suppose exactly half a 0 or so if we run for one iteration, success prob is half. If you run for k iterations, what is the success probability?
1 minus 1 half to the k.
Yes, so it's 1 minus 1 over 2 to the k. So note that this is actually pretty small, even for like moderate k, right? So if I want to be 99% sure, I would probably just have to do this like 7 times or something. So this is really, this is a very simple problem. So it has so this check actually works really well. Now, but the way I defined this algorithm, it's actually always going to return something which is 0, or it's going to loop forever, right? So this is a little bit different. So what I'm analyzing is a little bit different. I'm analyzing what happens if I ran it for exactly k iterations. This is not exactly what the algorithm is. But now I could ask, okay, so what is the expected runtime of this algorithm? Because the algorithm is always bound to be correct, because eventually you will find something with probability 1. You are going to find some element with AFI equals 0. But the question is, what is the expected running time? Okay, so this is what I want to now define. Okay, so for this we've got to brush up the basics of expectations, right? So expectation is defined for a random variable. Okay, so for any random variable. So in this case, the running time, which is number of iterations of the algorithm. This is a random variable, right? In the sense that if I had different outcomes, it will take different values, right? So if I had different coin toss outcomes, it will take different values. So that's why this is a random variable. Now we want to compute what is the expectation of the running time. So how would you compute this quantity? Yeah.
Sum over all possible k times the probability of success.
Probability of success at time k, right? Yeah. So this is by definition, it's the sum over all k. So usually expectation is defined in terms of an integral, but we have discrete random variable, right? The running time is either 1 or 2 or something. So it's sum over k going from 1 through infinity of k times probability that runtime is equal to k. Okay, so this is how you define the expectation of any random variable. Right? It's probability of x times probability that the random variable is equal to x. So good. So what is this? So
1 minus 1 over 2.
say that again.
Is that it?
Is that it? When is the runtime equal to k?
1 minus 1 by 2 to the k minus 1 times half.
Yeah, so two things must happen, right? One is the algorithm should not have succeeded until k minus 1, and it should succeed on the kth iteration. Okay? So that's why you get what you're saying. It is that it's basically it's 1 minus 1 by 2 to the k minus 1 times half, which is very close to this, right? It's basically 1 half minus 1 by 2 to the k, but this is the problem. Now, right, so now you can do this summation, right? So now what is the expectation of the running time? So you have expected value equals sum over k equals 1 through infinity of this point. so actually this is my bad. So this is not the probability that runtime is equal to k, right? So it's should drop with k. So yeah, my bad. So what is the probability that runtime is equal to k? So this is sure. So what is the likelihood that you have not succeeded so far and you succeed this time? Yeah. So this one is also 1 by 2 to the k. It's not 1 minus. It's yeah. So this is also 1 by 2 to the k, k minus 1 times this. Okay, in this case, things are exactly half. Otherwise, you would have had a different constant here. Okay, so otherwise, you would have had p to the k minus 1 times 1 minus p. Okay, so because exactly half the array is zeros, right? So that's why you get half of it. Okay, so this is actually exactly 1 by 2 to the k. Yeah, I got carried away. Okay, so this is k times 1 by 2 to the k. So actually, does everyone see why this probability is actually 1 by 2 to the k? Good. Why didn't you correct me? So anyway, so that's the idea. And now this you guys can compute. What's the, anyone know this off the top of their head? So I don't know either. It will come out to be a constant. I think it's 2 or 3, something like this. Okay, so this will come out to be a constant. Hopefully all of you know how to compute these things though. Right, so these are, yeah, so you look at, you call this something and then you look at k minus 1 times 1 by 2 to the k, subtract them. You know, the standard trick you would have seen in high school, right? So let's not do this.
2.
Yeah, so I think this comes out to 2. Okay, so alright, so that's the expected value of the running time. So the value is not very important, but the point is that the expected running time is just a constant in this case. So the expected time is a constant and you have this decay, right? And you have this success probability versus time thing. This is typically what we care about in randomized algorithm. Okay, so we say that, okay, so this is what it takes in expectation. This is how the decay is. And very often the expected running time, if you want a good confidence, you just need to be a little bit more than the expectation. Okay, so if you want a confidence of 99.9%, then you've got to be maybe slightly more than the expectation. Okay, so that's typically, we'll see examples of that, concrete examples of that. But that's the idea. So, but is this example clear? So we have success probability versus running time as something that grows like this. Okay, I'm sure this is, this is success probability. Finding this, and this is running time. Okay, this is 1 minus 1 over 2 to the k. And the expected value, expected running time for such a thing is 2. Alright, so that's the quick, so this is a very toy example of a randomized algorithm. Yeah.
So this is assuming that we don't remember the previous values of I, right? So we're sampling with replacement.
Yes.
So couldn't you improve it slightly?
Yeah. Yes. Then your running time will always be bounded by n at most, and then you can argue that if you've only found zeros, your probability would only increase, things like that. Okay, so yeah. So that's a good point. So is his point clear? That he's saying basically instead of just picking an independent I at every step, essentially try to pick one among the things that you've not seen. Okay. So it takes a bit more memory, but you can do it. So, alright, so that's good. So alright, so now we have, so these are a couple of things you should remember about analyzing randomized algorithms. So often when we think of deterministic algorithms, we had two things. we prove correctness, we bounded running time. Now there's a trade-off between these things. Usually these algorithms will be correct with high probability, and often there will be a running time. There will be an expected running time. And there will be a trade-off between these two. If you run for longer, you will be correct with greater probability. So that's one thing about analyzing randomized stuff. Now I wanted to give a couple of examples to say that this is not completely a toy problem. Okay, so these kind of things actually happen. So one is, so it's a cool application, it's called polynomial identity testing. So this is one example where coming up with a randomized algorithm is very easy, but we don't know very good deterministic algorithms for this. Okay, so that's why I want to mention this problem. So this is not supposed to happen. Alright, so what is this problem? So the problem is actually quite simple state. So you have two polynomials. You have P1, which is of, so these are variables x1 through xn. Okay, and these are polynomials of a certain degree. Okay, so think of an example could be like x1 squared plus x1, x2, x3 plus something. Okay, so every term is of this kind. And you have P2 xn, which is some other polynomial. And now, so these are polynomials. I mean, the caveat is that these are not polynomials over reals. These are polynomials over some finite field. Okay, if you don't know what these are just think of it as integers modulo p. Okay, so integers modulo 11 or something. So like, so does everyone know what modulo something means? Modulo. This is anyway just an example. So if you don't know, it's fine. I mean, yeah. So integers, you have integers modulo some prime, and all the computations happen in that finite field. Let's say. And now the question we ask is P1 identically equal to P2? So note that two kind of different looking polynomials, coefficients might by chance be equal, right? Just because they are in a finite field. There's only finite number of x's and x1 and x2s and so on. So you could arrange for things to actually become equal. So right, but the question is this identically equal to x1 through is P1 identically equal to P2? Okay, so that is it true? Is P1 of x equal to P2 of x for all x? X is now the vector. Okay, x is x1 through xn. And this is a problem for which turns out that the right way to do this testing is to simply say pick a random x, see if these polynomials are equal for that x. This is what you might guess, right? I mean, so sometimes you might say, oh, I'll look carefully at the coefficients, try to do something. But turns out an easier thing is you don't even need to construct all the coefficients. So you might say, when can I be given a polynomial without being given its coefficients? Can anyone think of examples like this? Is it possible to implicitly define a polynomial without actually giving you the coefficient? All of you would have seen examples of this, but you probably won't come to mind. Like, given some x's, I should be able to evaluate it, but in polynomial time. But I can't actually write down all the coefficients. Have you guys seen?
Machine learning, it's the feature vectors are, you can say they are very equal, like variables. And there is some function polynomial which
That's true, but very often you can't, like more in active learning settings you can do this. You can query a point and get the value. But typically you can't like give a query and get the answer, right? So But it's true. I mean, it's a reasonable example, right? But yeah.
Or we can think of a stochastic optimization problem.
Okay.
Like suppose there's a space and we just randomly throw particles and we sort of try to find the minimum.
Okay.
So we are essentially finding the minimum of the function without actually knowing what the function is.
No, but how does this have to do with the polynomial? I mean, so
So
why?
the
I mean,
function can be approximated to the polynomial function.
sure, but how do you evaluate that polynomial? The approximation, presumably, you know what the polynomial is, right? So what my question is: are there examples where you have an implicit polynomial? So, but so in the sense that given some values xi, I can actually compute it, but you can't actually write out all the coefficients. So let me give an example, then you'll see what I mean. Okay, so what I mean is you could have a polynomial which is defined as the determinant of a matrix whose entries are something like, oh, I have x1, 2x2, x3 plus x4, something like that. And it's the determinant of this matrix. In principle, there is a polynomial, right? Because, I mean, if I expand out the determinant, it will be a polynomial. But I can't literally, but if I expand it, I'm going to have exponentially many coefficients. But now if I tell you what x1, x2 to x3, xn are, I can always plug them in. Now I just have numbers. I can compute the determinant of a matrix in polynomial. So this is kind of the applications in which people use this kind of a thing. So you have polynomials that are too big to write out, and now somebody tells you they are both equal. How do you test? You pick a random point. People in electrical engineering use this a lot because they try to come up with very nice compact representations for circuits. So you begin some circuit and say, oh, the computation that this circuit is doing can be mimicked by this other circuit which is much smaller or much nicer, whatever. Right? So turns out to compare these things, the best way to do, or a really good way to do, is just to pick random entries. And so there is something called the Schwartz-Zippel lemma, which essentially tells you that this is actually a good way of doing it. Okay, so yeah, I just want to mention that this polynomial identity testing problem has applications in circuit checking and stuff. There are also some nice theory applications of this, like computing matchings, but don't think. Actually, the textbook has that. So, that's a good application to matching. Okay, so this is just something that I wanted to mention. Okay. And and the reason I mentioned it in the context of the previous problem is that it's kind of like the previous problem, right? In the sense that you can think of all possible x values as being array elements. And it's saying that if the polynomials are not identically equal, then in many spots they actually differ. So in that sense, it's exactly like the previous problem. So, yeah.
In the problem of the determinant, what should we, I mean, I don't understand what is the difference between the problem we are computing, then the determinant, and the solution without huge expression.
Oh, so the point is, suppose I gave you two matrices, both of which have some x's in them. Okay, so one is x1, x2, something like this. Question is determinant of, so you have a polynomial which is the determinant of the first matrix. That's a polynomial, that defines a polynomial. And you have another polynomial which defines the determinant of this other matrix. Maybe this other matrix is actually bigger in size or whatever. Question is, are these two polynomials the same? Identically equal? If you could expand out all these polynomials, then you can actually compare coefficient by coefficient.
Yes.
But if I had a determinant, the only way to expand it is by using exponentially many terms. But on the other hand, if I have concrete values to excise, you can plug them in. Now I have determinant of a numeric matrix, which I can compute in polynomial time by doing Gaussian elimination or something. and now I can check the values. So this is one trick that you can use to check if, now you can say, okay, maybe I was unlucky, maybe for the values xi I picked, maybe these two are equal, right? But what you can show is that if the polynomials are indeed unequal, then for most choices, you will actually, they will actually be different. So that's why this is used in circuit checking, because there you want for all inputs these two circuits to compute the same function. Okay, so yeah, and you check this by saying, oh, I'll check this for okay, so we don't have time, so we won't do primality testing. Or maybe I'll just mention what the problem is. So this is again a non-standard application. Okay, so it's you're given an n-digit number. Okay, so suppose I gave you this number. So they ask you, is this prime or not? Okay, so it takes me n space to write down an n-digit number. So you want a polynomial in n time algorithm. And this was a very big open problem. Now it has been solved. Okay, so and the reason we care about it is because it's a basic function of the number. We know we can add, multiply, take GCDs of n-bit numbers, n-digit numbers in poly n time. So can you check if it's prime or not? Can you factorize it? Those are the questions you can ask. Right? So that's why we care about these problems. And right, so turns out one of the earliest algorithms for this is a randomized algorithm. Okay, so this was in the 70s. This is by Miller and Rabin. Okay. So yeah, so what they essentially said is that you start with some number less than x less than this, and you do some powering, and they had what is called a Fermat test. Okay, and they showed that if a number is composite, then this test fails for at least half the numbers between 0 and n minus 1. 0 and this number n. So this again is exactly like this toy example that we said, right? So somehow, if the number is composite, then this test will figure out that it's composite with very high probability. Okay. If the number is prime, then the test will always fail. Okay, so you do this test for a bunch of times, and then you are in good shape. Okay, so that's yeah. So again, we won't go into this. Is a very number theoretic thing, but I want to give you a sense of what type of things you can do with randomization. So good. So one thing that we'll actually see is median finding. So I'll introduce the problem, and we can do this next time. Okay, so this is similar to quicksort. Okay, and the question here is, we've seen median finding in deterministic settings, right? So we know we can solve this in linear time, but that algorithm was rather tricky, if you guys remember. Okay, so we were dividing into groups of 5 and doing some stuff. Did we see this?
You mentioned it, yeah.
Oh, okay. So maybe I did. Okay, we saw this last year. Okay, never mind. Yeah. So, so median finding can actually be done even deterministically in linear time. Yeah, but turns out there's a very simple algorithm for this. So A1 to AN. So these are just some numbers that you are given. They are not sorted. And the question is, suppose n is odd. The question is, find the mid-level. So what I mean by that is, suppose you sorted it and you actually want to look at mid-level. So no, we did actually see. We saw how you select the kth smallest element. I remember. So yeah, go check with divide and conquer notes. So yeah, so that's what we did. So, and the goal is you want to find the mid-level. And if you remember how we did this, we said, oh, I have a more general algorithm that finds the kth smallest element. We did by divide and conquer. Basically, divide it into divide it cleverly and reproduce it. So now I want to give a very simple algorithm which tries to essentially pick a random element and divide the array into two pieces. So it's what is called a randomized divide and conquer. And we'll see the analysis and the detailed algorithm next time. Okay, so this is it's a very clean algorithm. It's something that you might actually implement, and it works pretty well.